Um, how old are you? How tall are you? The answer to these questions are measurements. Measurements are important in both science and everyday life. It would be difficult to imagine doing science without measuring anything. What is scientific notation useful? Or why is it useful? Well, scientists often work with very large or very small numbers. Astronomers estimate that there are two followed by a lot of zero stars. That's actually 200, what's that, trillion? Yeah, so this would be, whoops, let me back up. This would be millions, 200 billion stars in our galaxy. So, scientific notation is a way of expressing a value as a product of a number between 1 and 10 and the power of 10. For example, if we wanted to say 300 million meters per second, we would just write that as 3.0 times 10 to the 8th. Notice that there are 8 zeros here, and we're multiplying 10 to the 8th power. The exponent 8 tells you that the decimal point is really 8 places to the right of 3. For numbers less than 1, we use scientific notation, but this time we use a negative exponent. So, for example, the average snail's pace is 0.00086 meters per second. In scientific notation, that would be 8.6 times 10 to the negative 4. What the negative 4 means is that we're going to move the decimal 1, 2, 3, 4 spaces to the right. So if it starts off as a decimal, your power of 10 will be negative. The negative exponent tells you how many decimal places you are to move to the left of the 8.6. So in other words, if this was 8.6, I really went 1, 2, 3, 4 units to the left to get the actual number from scientific notation. To multiply numbers written in a scientific notation, you multiply the numbers as they appear before the multiplication signs and add the exponents. The following example demonstrates how to calculate the distance light travels in 500 seconds. So this represents the speed of light. That's at 3 times 10 to the 8th meters per second. And then 500 seconds is really 5.0 times 10 to the 2. So what we do is we multiply 3 times 5, which is 15, and then we add up the exponents for the powers of 10. 8 plus 2 equals 10. Now, I don't want this as 15. I want it as a number between 1 and 10, so I'm going to move the decimal over 1 unit to the left. When I do that, I have to add that 1 in. In other words, 10 plus 1 is 11. So my answer is 1.5 times 10 to the 11 meters. This is the distance between the sun and the earth. When dividing numbers written in scientific notation, you just divide the numbers as they appear and then subtract the exponents. So, for example, if I wanted to figure out 1.5 times 10 to the 11 divided by 3 times 10 to the 8, what I would do is I would say 1.3 divided by, 1.5 divided by 3 times 10 to the 11 minus 8. I would get zero point 0.5 because 1.5 is half of 3.0. And then 11 minus 8. Now, again, I'm going to move this decimal one space over here. When I move this to the right one time, I'm going to subtract, in this particular case, that one space. So I get 5.0 times 10 to the 2. For scientific notation, let's do an example problem. So a rectangular parking lot has a length of 1.1 times 10 to the 3 meters and a width of 2.4 times 10 to the 3 meters. What is the area of the parking lot? Well, we're just going to multiply the length times the width. The length was 1.1 times 10 to the third, and the width was 2.4 times 10 to the third. So remember, the area is length times width. And so I'm just going to plug all this stuff in. I'm going to multiply the 1.1 times the 2.4. That gives me 2.6. And then I'm going to add the exponents. This 3 plus this 3 gives me 10 to the 6. And then meters times meters, don't forget your dimensional analysis. Meters times meters is meters squared. Did my answer seem reasonable? Yeah, I could plug it in a calculator and double check. So here are some example problems that they want us to do in a calculator. We're going to skip that for now because I have a worksheet of problems that I'm going to have you guys do. What units do scientists use for their measurements? Well, scientists use a set of measuring units called SI, which is the International System of Units. Now, you might say, why is it SI and not IS? Because it's in a foreign language. Only in the United States do we put the descriptor in front of the word it's describing. So, SI is the abbreviation for System International de Units. Well, this is the translation of that. So basically, SI is reversed from the metric system. It's French. Scientists around the world use the same system of measurement so they can readily interpret one another's measurements. Yeah, just it's the metric system, sort of. Um, if you told your friends you had finished an assignment in 5, would it mean 5 minutes, 5 hours? So this is important, kind of having a universal standard or metric is a better word for measuring things. So always express measurements in numbers and units that have a clear meaning. Okay, students, these students' temperature measurement will include a number and a unit. In this particular case, is Celsius. However, Celsius and Fahrenheit are not the SI unit. It's actually Kelvin. So what are these SI units? Well, there's seven metric units known as the base units. Um, the base unit for length is meters. The base unit for mass is kilograms. And here's the rest of them. Temperature is Kelvin, capital letter K. Time is second, believe it or not, even though we use hour and minutes a lot. When we're doing science, we want it to be in seconds. The amount of substance is a mole. We'll talk a lot about that. When we get to the physics part, we'll talk about electric current. That's amps. And then luminous intensity, candela. And these are all the abbreviations listed here. Additional SI units called derived units. For example, we're measuring length, but volume is a measurement of length times length times length, three-dimensional length, right? Density is the ratio of the object's mass to the volume. How much stuff per volume? So here are some additional derived units. Now, we call them derived because they're some variation of the 7. Um, area, that's a derivation of length. Volume, that's a derivation of length again. Um, Density, that's mass and length and length and length. Pressure, that's mass, length, and time. Energy, that's mass, length, and time. Hertz, which is like a frequency, that is actually a measurement of time to some degree. And then electric charge, that's amps versus or times time. So, and these are the appropriate symbols or the units in which we use to measure those things. So to derive an SI unit for density, you divide the base unit for mass by the derived unit for volume. Um, Dividing kilograms by cubic meters in SI unit gives you the density of kilograms per cubic meter. A bar of gold has more mass per unit volume than a feather, so gold has a greater density than a feather. Metric prefixes. Now, we're going to do a whole worksheet on this too. Because we measure big and we measure small, and we use scientific notation, which are powers of 10, we have these prefixes that let us kind of give an idea as to what we're actually talking about. So, giga, mega, kilo, and there's some other ones too that aren't listed, but those are just prefixes for multiplying by a power of 10. Kilo means 1,000, mega means million, giga means billion. Okay. And then when we multiply by something by a fraction, or 1 divided by 10 or 1 divided by 100, deci is 1/10, centa is 1/100th, Milli is 1/1000th. Micro is 1 1/10,000. Well, it's 10 to the negative 6. Nano is 10 to the negative 7th. So the micro is 1/1 millionth and nano is 1/1 billionth. So when you hear things about nanotechnology, they're talking about things that are 1/1 billionth of a meter. Tiny. For example, the time it takes for a computer hard drive to read and write data in the range of thousandths of a second is about 0.009 seconds. Using the prefix milli, you could say that 0.009 seconds is 9 milliseconds. Okay. Metric prefixes can also work for larger things. For example, the distance of 12,000 meters can be written as 12 kilometers. Sometimes that's helpful to work in that direction. Lastly, we're going to talk about conversion factors. So because the formulas that we're going to be using only work with SI units, especially physics, although this knowing how to do conversions is very helpful in chemistry as well. A conversion factor is a ratio of equivalent measurements. In other words, 1 kilometer is equal to 1,000 meters, and 1,000 meters is equal to a kilometer. But these two, written in ratio form, in other words, this equals this, and this equals this, can be used as a conversion factor. The way that we choose which conversion factor we use is based on what we start off with. So in this particular case, we want to convert Mount Everest, which is 8,848 meters, into kilometers. To do that, I'm going to write down what they give us, 8,848 meters, and I want to convert that to kilometers. I have to choose the second option or the first option because I want the meters to cancel with the meters, and consequently, that leaves me with an answer in kilometers. This times 1 is 8,000 blah 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 divided by 1,000 gives me 8.848 kilometers. And we're going to do a whole worksheet on this. Lastly, I thought the last thing was the last thing we were going to talk about. What does or how does precision of measurement affect the precision of scientific calculations? So this is important. Precision is a gauge of how exact a measurement is. Significant figures are all the digits that are known in the measurement, plus the last digit that is estimated. So precision of a calculated answer is limited to the least precise measurement used in the calculation. So the more precise time can be read from a digital clock than from an analog clock. Now, what that means is that here I don't know what fraction of a second I'm dealing with. Well, here this is hours, these are the minutes, and these are probably the seconds. Okay, here I don't know what the seconds are because there is no second hand on the clock. That's basically what they're saying. So the most precise answer would be this one because at least I know up to the second value roughly. Now, it might be between 15 seconds and it might be between 16 seconds. However, here, I don't know what seconds it is. So I'm off by a minute here, possibly. It could be 301, could be, you know what I'm saying? But here, I'll know precisely based on the seconds. So it's a more precise. The least precise measurement in the calculation has 3 significant figures. So then the answer must have 3 significant figures as well. What they're saying is that if I want to calculate the density, that's a weird way to put that, but basically, I'm going to have to make a calculation. I'm given 2 measurements. Volume has 1, 2, 3 significant figures. The mass has 1, 2, 3, 4. This is the least precise. When I do the math, I get this number. But because this is the least precise, I'm going to have to round this to 3 decimal places, 3 significant figures, not decimal places. Rounding 3 significant figures, the density is 7.86. So I take this 5, look over here. 7 is greater than 5, so we round up to 7.86 cubic centimeters, grams per cubic centimeters. Accuracy this is where kids get confused. Precision is determining the least precise measurement, where accuracy is the closeness of the measurement to the actual value being measured. For example, suppose a digital clock is running 15 minutes slow. Although the clock would remain precise to the nearest second, the time displayed would not be accurate. So accurate is yeah, that's a really good example, actually. So, a thermometer is an instrument that measures temperature of how hot an object is. Most of you guys should know this, but we'll go over it just in case you don't. Most thermometers have a tube. They have some sort of colored liquid that increases as the temperature increases and contracts as the temperature decreases. The bulb is the reservoir for all the liquid, and usually there's a scale. To the left is the temperature in degrees Celsius, to the right is the temperature in degrees Fahrenheit. The scale indicates how far up the liquid moves to determine the temperature. So basically, the liquid rises in the tube and expands as the temperature increases. It also decreases. Now, if it's a really wide tube, you need more liquid, obviously. If it's a very narrow tube, the scale is adjusted so the temperatures are the same no matter what. Okay. So, two temperature scales that you're probably familiar with are Fahrenheit and Celsius. A degree Celsius is almost twice as large as a degree in Fahrenheit. You can convert one scale to the other by using these formulas. Now, the reason that they have two different scales is there were two different scientists, Fahrenheit and Celsius. They did a lot of measurements of temperature. These are the scales that they come up with. Same with Kelvin, which is the metric standard. So the SI base unit for temperature is actually Kelvin. The formula to convert from Celsius to Kelvin is this. You basically add 273 degrees to whatever the Celsius temperature is. And that's it. So if we were to look at simple things, water boils at 212 degrees Fahrenheit or 100 degrees Celsius or 373 degrees Kelvin. Kelvin's really nice for things that are really cold. Okay. The human body, your temperature is 98.6. In Celsius, that would be 37. And in Kelvin, that would be 310. Your average room temperature is about 68 degrees. I would say 72, but we'll just go with this chart. That's about 20 degrees Celsius. And then Kelvin is 293 degrees. Water freezes at 32 degrees Fahrenheit, 0 degrees Celsius, and 273 degrees Kelvin. And we're going to skip the assessments. That's it. That's all I got for you today.